finished the flat plate, right? And we're about to talk about the thin airfoil theory. So, okay, what did we do? So, you have your flat plate, and you have your infinity, and you take alpha. We said, well, we have the circulation, and we found how much circulation is generated, and how much left, okay? But then we said if we have a more complicated shape, what are we going to do? So we said there are two methodologies, the method of singularities and the method of conformal mapping. So we had an example for the method of conformal mapping, which is this guy, because we solved it using the flow around the circular cylinder. So let's talk about the method of singularities. So in particular, for the method of singularities, you replace your body with a distribution of singularities. So in particular, we will use it to solve the flow around a thin airfoil. So we'll talk about the thin airfoil theory, skeleton theory from Germans, which is the theory, these are the same thing, lifting vortex sheet. So you have a sheet of vorticity that is providing you all the lift. So what do we have here? We have an airfoil, exaggerated of course. And this is your core line. The line connected the leading edge and trailing edge. So this is your core seam. The mid, the line that is dividing your airfoil, the thickness of your airfoil. This is what we call the camber line. So this is y camber as a function of x. But this is x, okay? And this is y. So as you can see, because the airfoil is wrapped around the camber really represents the skeleton of your airfoil, and this is why we're talking about the skeleton theory, or it's called skeleton theory. So we'll neglect the effect of the thickness, or assume that it's very thin, so that the effect of the thickness is negligible, and we will determine the lifting characteristics of the following. Just the camber line. And again, this is a review. So this is C, this is your X, this is your Y, this is the maximum camber, and this is the ordinate at any X. Okay? The method of singularity, so this is the shape along which I'm going to solve my problem, my flow field. Here is your infinity. Again, I'm exaggerating. This is your alpha, okay? So I want to solve the flow field around this shape. Okay, the method of singularities dictates that you replace your shape with singularities. Here we will choose vortices. So we have gammas, okay? Two-dimensional, two-dimensional. So this, the maximum camber is small with respect to C, then you can consider this distribution as if it's on the x-axis. So this is x, this is y, this is your skeleton. But my distribution of vortices, gamma now is a function of x, it's on the x-axis, okay? This distance is much smaller with respect to that distance. Remember, this distance is the disturbance to the flow, and we are linearized the theory, tension flow, so it's convenient to consider small disturbance. Any question about the problem setup? If you have any question, please. Any question? This is a review again. I'm sure that you have seen that in airfoil theory in your undergraduate or your graduate course. Next lecture today is the new stuff. Any question about this? Okay. So you will replace your shape, this red shape, with distribution, this blue distribution of vortices. Of course, the distribution is unknown. And by replace, I mean just remove this guy. I don't need it anymore, okay? The flow field will be as if you have U infinity plus some vortices. That's it. So the flow field everywhere will be by superposition of uniform flow and distribution of vortices, okay? So this is unknown. The right distribution that represents the body is unknown. How can we determine it? This is the point. So, yes, David?
This approximation is valid even for very highly cambered airfoils?
No. It's very highly. So this is typically around 10% of the flow. So that's okay. If it's very highly cambered, you're saying 50% of the core, so it's really very large disturbance. No, this theory will fail.
So 10% or less is fine.
Yeah.
Okay.
So, okay, we're looking for the right distribution. Because if I have this guy, if I have how much vortex here, there, okay, I know the flow field everywhere, I will use the superposition. And if you know the flow field everywhere, you know the pressure over your shape, so you can integrate and get the forces, okay? Remember what we're solving here, in general. We're solving potential flow, right? What's the governing equation for potential flow? What's the governing equation? Come on guys, what's the governing equation for potential flow? What? U? No. This is the potential, complex potential of uniform flow. I'm saying potential flow in general. Any potential flow, what's the governing equation? What's the governing equation? Come on. What is the thing? Because this is this is why we're doing the review. I mean, you have seen the potential flow before, and this is why I'm doing the review, because this information is essential to be fresh and vivid. Why we were able to do all this stuff? How we were able to arrive at CL equals 2 pi alpha? What's the governing equation that allowed us to do that? What's the governing? Say it again, sorry. Laplace is not transform. Laplacian. I mean Laplacian. Laplace squared phi equals 0. This is the governing equation. Or Laplace squared psi equals 0. Laplace squared f equals 0. This is the main governing equation of a potential flow. This is what we're solving. But this is a PDE. So you need boundary conditions. So that's subject to what? Subject to what? What are the conditions? So we discussed this heavily. We did not discuss the boundary condition, but you have seen it before. Subject to the no penetration boundary condition. Okay? What do we mean by the no penetration boundary conditions? That the flow normal to the surface is 0. The flow component normal to the surface is 0. That the flow doesn't penetrate the surface. The name is very expressive. Sometimes it's called the kinematic flow condition, because it's a kinematic condition, not dynamic one. Okay? Any question about that? The singularities that we use, the point vortices or point source, point sink, they automatically satisfy this guy. Okay? They automatically satisfy this guy. So, whenever you put just distribution of vortices with any strength, I don't care. As long as the induced velocity is gamma over 2 by r, this flow field automatically satisfies Laplacian. So U infinity automatically satisfies Laplacian, the distribution of vortices automatically satisfies Laplacian, so what's the only thing that I did not satisfy? What's the only thing left that I can make use of? So this is my original problem statement if you want to solve it numerically. Solve this PDE subject to this boundary condition. Okay, we said we're going to solve it this way. We're going to put some distribution of singularities. They automatically satisfy the differential equation. So what's the left thing that you can make use of? Come on, guys. How many pieces of information do we have? Ignore anything. In potential flow, how many pieces of information do we have? What do we have at our disposal? What do we have? Just look here. What do we have here? What do we have? What do we have? Come on. What do we have here? Okay, at least we have the Pascal phi equals 0, right? This is one thing. What else do we have? What else do we have?
The boundary condition?
The boundary condition, that's it. It's nothing. It's your differential equation subject to boundary condition. Okay? It's nothing. Nothing more. What I'm saying is that this guy, the flow field due to gammas is gamma over 2 pi r. This automatically satisfies the differential equation. So what's the only piece of information that I didn't make use of? What's that? The boundary condition. So the only piece of information that I can make use of to determine how much gammas, because any gamma of any strength, as long as it's the potential gammas, whose flow field is gamma over 2 pi r, will naturally satisfy here. So put them as maybe tens, all of them, they are equally strength, they will satisfy the differential equation. Any distribution, they will satisfy the differential equation. But what is the right distribution that resembles the body, that represents the body? Well, this has to do with the body. So what's the only piece of information that I didn't make use is the boundary condition. And the boundary condition indeed has to do with the body. It says that the normal component to the body is 0. So this piece of information will help me get the gammas. Okay? Any question about that? How many equations does this represent? How many equations? Can you think about it? How many equations then? So does this help? How many equations left?
Infinite.
Infinite number of equations, because v at the initial point is 0, at the second point 0, third point 0, have infinite number of points on our body. So this is infinite number of equations. How many unknowns we have? How many unknowns? So what is the unknown? What's the main unknown here? What I'm looking for? What's the main unknown?
Gamma.
Gamma. I'm looking for gamma. If I have gamma, I'm done. Right?
Yeah.
So the flow around the circular cylinder, this guy was equal to U infinity plus doublet plus gamma, right? And the radius of the circular cylinder dictates how much doublet strength. So we got this guy. The Coulter condition dictates how much vortex. So if you know all your elements, you're done, right? Because then you can get the velocity at any point by adding the velocity to each one. Here we're solving it in another way. We're saying, okay, I will not pick the right elements, I'll put any elements you like. Vortices all over the way. Okay. But with unknown strength, if you know them, you're done. The problem is done. Okay, how much is this guy? We don't know. Okay, how many unknowns are these? Well, they are infinite. Why? Because it's gamma at each point. So we have infinite number of equations, infinite number of unknowns. Okay, so if it's infinite number of equation, infinite number of unknown, what kind of equation do you expect to get? Can you guess? Well, if it's 3 equations and 3 unknowns, we expect an algebraic equation, right? This is one type. So if I have a function that is unknown, so well, if it's either a differential equation or integral equation, right? So I'm not expecting an algebraic equation. So let's see, whatever it comes. What is my main condition? It's this guy. Get the velocity component normal to the surface at each point equated to 0. Hopefully this is an equation in gamma, solve for gamma, we're done. Okay? Please, if you have any questions, stop me. Again, this is review, so we're reviewing it. So if you have a question, stop me. Any question about the big picture? Why we're doing this? Please, you never feel shy. Come on. Okay. So this is easy to do. Well, let's see here. So here is my x-axis. Here is the origin. So this is y. So x is measured from here. I have a point vortex, one of these guys. This is at the distance x dash, maybe some x. And if it's at the distance x dash, it's this distribution, the vortex strength times delta x dash. So I'm taking an element here, small element. Okay. So this is your vortex, point vortex. And at the generic x, do it like this. We used to do the gamma u, gamma of x dash dx dash. So can you tell me how much velocity induced at this point by this guy? In what direction? It's downward, right? How much is it? How much is it?
Gamma x.
So gamma, whatever gamma, over 2 pi distance, right? What's the distance? What's the distance?
X minus
X minus x.
X minus x bar. Okay, very good. We got this guy. Well, I need the normal component of the surface, so this is maybe here. Maybe this is my camber. Okay, whatever. Assume any funky camber. At this point, we need it just to show things.